So now we will move to the second part to the second section of the article. Sorry, I'm getting sweaty. Okay. So the section, the second section is called Lattice Tool for QCD. So what does the lattice do for us? Basically, you use it to estimate or calculate correlation functions. So something that would normally be represented by the operator at x, operator at y. So kind of like a green function equals to this. So this could be any pair of operators. There could be more than two operators, of course. It would have to be a 2-point correlation function. It could be a 3-point correlation function. And the main point is that this is done non-perturbatively. So normally, for example, in QED, we can calculate those correlation functions by just using a perturbation on the coupling constant. So lattice can do this same calculation, but non-perturbatively. And how is that done? Well, you put everything on a lattice. So let's say this is point x. So there are discrete points on your lattice. And then there's point y over here, or here. There is y. And then you do Monte Carlo sampling. Monte Carlo sampling. So what do you sample? You sample the configuration of your matter fields. So Monte Carlo sampling following the Lagrangian of QCD. So you sample over different configurations that your gluon fields and your fermion fields might have. Gluons and your fermions. So what you do is basically you take your lattice, and then following the Lagrangian, there's a configuration where your gluons are doing something. They have certain value, and then the correlation, because it depends on the value of your fields at different points, then for a specific configuration, the values of these operators have a specific value, and then the total value of the correlation function is just basically going to be given by a specific configuration. Let's say if the gluons and fermions were simply arrows, specific configuration weighted by the Lagrangian plus another configuration weighted by the value of the Lagrangian in this other configuration. and so on. So of course there's a really big number of configurations, because gluons are not just spins that are up and down. Gluons have lots of degrees of freedom. They are basically so they have way more degrees of freedom. They have a continuum of degrees of freedom, and then you sum over all, or as many as you can, using Monte Carlo sampling. So you sample over the most important values according to the Lagrangian of QCD. Okay, so that's the lattice. Big idea. Then the second part is that there are of course approximations. Lattice. So instead of approximating in the value of the coupling, you have finite A, L, and different masses of your stable hadrons. For example, a different mass of your pi. So this is the lattice. These are your lattice points. This is A, this is L. Right? But you can obviously you can come and say, okay, well, I can study g of x, y as a function of A, L, and m pi, where m pi is the mass of the pion, and then take limits. So the continuum limit, the infinite volume limit, and then mass pi to 140 MeV. So as long as you're taking the limits appropriately, this should work. So for example, for stable hadrons, they are eigenstates of the QCD Hamiltonian. Stable. So that is nice because you can study them very easily on the lattice. You just have to mass of the stable particle. Stable. So you can show that G T1, T2 is going to go like e to the minus mst, T1 minus T2, when for values of T1 minus T2 very, very large. So using that property, then you can study their the mass of stable particles, but you can also study their electroweak behavior, their form factors. So you can search for, so in the stable sector you can search for, even nowadays this is done, search for beyond standard model physics by checking how experimental data differs from QCD using lattice. However, unstable hadrons are not eigenstates of the QCD Hamiltonian, so you have to be more careful on how you can study them. So unstable hadrons show up in scattering amplitudes as enhancements, so you better be able to do scattering in a finite volume. So that's the next section of the paper. So for some questions up to here. So that was for this part. So the next section of the paper is scattering in a finite volume. So in this part of the paper, they say, okay, imagine a one-dimensional scattering. No, the one-dimensional quantum mechanical system. So if you imagine a one-dimensional quantum mechanical system where the potential between the two particles is finite range, so you know, it has some finite range. Outside of the potential, then your particles are going to be free, and it's only when they are close together that they interact. Then you can go to the center of mass, and then the wave function factorizes into the movement of the center of mass and the relative movement of the two particles. So the relative, there's going to be the total wave function that depends on each of the particles. That's going to get factorized into the center of mass movement and then the relative movement. So this relative movement is of course dependent on the difference between x2 and x1. So if you think about that wave function, that is going to, so if this is xr, and let's say the potential is here, so this is br, dx, b of xr, then the wave function outside here is just going to be, this is supposed to be e to the, so it's just a free wave function, the potential is 0. Here we don't know whatever it does, and then here it has to be still a free wave function. So because there's a potential, then there's actually a phase shift, right? So if your incoming particle, in a sense, this can be seen as an incoming particle into your potential, and then it goes out. So if it has a free-form functionality after crossing the potential, then it acquires a phase shift. And that's, you don't know anything about here, but because it's finite range, this is the way you can parameterize all the interaction. So what happens when you go into a finite volume? Well, if you go into a finite volume, then this becomes periodic. So this is xr, this is your potential, and then your wave function has to be periodic. So if your wave function was ekx, then after crossing the potential, it's going to be ekx plus delta k. But then when you come back to here, you need to have that x plus l is equal to 5x. So you have that e to the a k x plus l plus delta is equal to e k x. So you're here, you come back here, and you have to acquire to have the same wave function. So therefore, you can show that this is the same as requiring that k has to go as 2 pi n over L plus delta k over L, where n are integers. So this is the finite volume. So K is of course proportional to the energy, K squared over 2m. So when you are in a finite volume, K, so in this case K could have any value. This is just a parameter of the total energy, and your total initial energy could be whatever you want. However, when you're in a finite volume, you get quantized, and K can only take certain values that solve this equation, where this is the phase shift and this is the energy. So so let's say we plotted the energy against the volume. So if you imagine, we can plot energy. So let's say the phase shift was 0. So you would have one level here, which is n equals 0. So if n is equal to 0, this is 0, k is equal to 0. But you would have other levels too. So n equals 1, n equals 2, equals 3, and so on. So everything blows up when L goes to infinity, but then they decrease. So, but what happens if delta k wasn't equal to 0? So if delta k is not equal to 0, then your system might behave in a different way. So as a function of L, the energies that you will find might be, an energy that's slightly dependent on L, then something like this, where this n1, this n2, this n3. So if you somehow were able to find the energy spectrum of your system for a given value, for several different values of L, you can trace these lines back, and by doing that, you might distinguish different cases. So for example, if you calculate the energy of the different energy values of your system, and you get this pattern, so imagine you just get the black dots instead of the lines, just get the black dots instead of the lines, you can more or less back engineer what was the phase shift according to the black dots. And then just the last remark. So this was 1D. So 3D is a similar idea. It's a little bit more technical how this is done in 3D, but it's a similar idea. And then the only caveat is that the rotational symmetry is broken by the lattice. So your lattice, the rotation symmetry is broken. So spin is not a good quantum number. So that's the only thing you have to take into account.